Now, before we go on to the final part of statistics, I want to refer back to part 2, where we were calculating 95% confidence limits. And we said that these limits were equal to the mean plus or minus 1.96 times the standard error of the mean. So where do we get this 1.96 from? Well, if you are very observant, you will have seen in your t-tables at the column of infinity and 0.05 probability that the number in the t-table was 1.96. This is what we use when we have a large sample. If we have a sample less than 30, then we apply the formula n minus 1 degrees of freedom and look up the t-value at that row. So if you did your homework with the ruler dropping experiment and you wanted to know the 95% confidence limits for the 10 trials with your right hand, then you would apply the rule n minus 1, that's 10 minus 1 is 9. You would look up 9 degrees of freedom at the probability value of 0.05, and that would give you the t-value of 2.262, and you would use this rather than 1.96. Now, if I wanted to plot a graph to show my neighbour the findings of my hedge data, it's quite straightforward. Obviously, the independent variable is the side of the fence, so that will go along the x-axis, and the dependent variable will be the size or the area of the lease. So what we do is we plot the two means, then we add on the 95% confidence limits, and we draw that as a little line above and a little line below the points, and then we simply join the two bars with the straight line. As a rule of thumb, if the 95% confidence limits overlap, it suggests that there is no significant difference. Whereas if they don't overlap, it suggests that there is a significant difference. But we do a t-test just to check. So we got the hedge situation sorted out, no problem. And I thought, I'll relax, I'll come outside and I'll play a little game of Monopoly. And I'll set up my game here, and my old friend Andy Bell, he's playing in his house on his board. Trouble is, I think he's cheating, because every time he seems to need a 6, he gets a 6. I think his die is loaded. But how could I prove that? Well, in all probability, the numbers 1, 2, 3, 4, 5 and 6 should appear just as often as each other. So I have an expectation of what the probability of each number should be. And if I measure this probability with the observation and I compare those two, it's a bit like our t-test. We can see if there's a significant difference. But this time it's between an expected ratio and an observed ratio. The test we use for this is called the Chi-squared test. By the way, does the sound of that fountain make you want to go to the toilet? So probably the easiest way to take you through the Chi-squared test is to use the example of the Monopoly game. So as you can see from the table, we have in the left-hand column the number on each face of the die. Then in the second column, the number of times each number was thrown. In the third column, we've got the number of times you would expect each number to be thrown. How do I know that? Well, there was a total of 60 throws, 6 faces, 6 into 60 goes 10. In the next column, we take the expected frequency away from the observed frequency. Then we square that, which makes all the numbers positive. Then we divide by the expected frequency. And finally, we add all of those up to give our chi-squared number. So just like before when we were carrying out the t-test, we first of all formulate our null hypothesis. Then we look up the chi-squared value in a set of tables, but are known as the chi-squared tables. The number of degrees of freedom is given by the number of different dice possibilities minus 1, which will be 5. And again, we apply Rowley's LSD rule. If the probability is less than 0.05, then there is a significant difference. And if it is greater than 0.05, then there's no significant difference. So what does this mean for our calculated value of 13.6 for the chi-squared test. Well, as you can see, it fits into a probability between 0.05 and 0.01, which is still less than 0.05, so that means that there is a significant difference. So we reject our null hypothesis and we conclude that Andy Bell is a dirty, rotten scoundrel.